Good afternoon and welcome to Web Cache Entanglement, Novel Pathways to Poisoning. Have you ever thought you understood something and then realised that what you understand is actually only 1% of the total? Or have you ever found a vulnerability that wasn't quite exploitable, an exploit chain with a missing link? In this session, I'm going to share with you some advanced techniques to find some seriously esoteric cache behaviors and combine them into glorious exploit chains to turn junk vulnerabilities into criticals. I used to think that I understood most of what there is to know about how caches work and how to poison them, until I stumbled on a small information leak. On systems running Akamai, if you send a certain pragma value, then they'll come back at you with their cache key in the response headers. And the value of this key was a bit different from what I expected. But more concerningly, they don't just come back at you with that one header, they actually give you two cache keys which don't quite match. And if you add another pragma value, you get a third cache key. But, I'm sure things are simple, right? We just need to identify which of these cache keys is actually accurate. Well, is it the humble cache key? Is it the extended cache key for internal use only? Or is it the true cache key? After extensive research, I can tell you that the answer is none of them. Not one of these keys is entirely accurate. But if we assume that there's some kind of element of truth in them, then they still leave us with some quite serious questions, like, where did my parameter go? It's in my request, but it's not in any of the keys. Where did this Akamai transform parameter that I didn't send come from? And why is it in some keys but not other keys? What's this double underscore thing about? That looks kind of shady. And are other caching systems this quirky? Following up on each of those questions led me to an exploitable scenario, which I'm going to share with you today. First, I'm just going to recap the basic cache poisoning concept and show how this research diverges from classical cache poisoning techniques. Then I'll share a methodology for finding these new types of issues, share a whole bunch of case studies where I've applied the methodology to find real vulnerabilities in sites that have bug bounty programs, and share some tooling to make your life easier. Then I'll talk about how to prevent these attacks, wrap up, and take roughly 5 minutes of questions. Caches work by saving copies of web pages in order to reduce load on the backend system. And web cache poisoning is just a general term for when you trick a cache into saving a harmful page and serving it up to other users. How do you poison a cache? Well, caches map requests to responses using something called the cache key, which is the subset of the request that they think is actually important. Generally, this includes the host header and the request line, but it doesn't include random other headers like the ones that I've highlighted in orange on this slide. So a classic cache poisoning attack is you simply put your payload in one of the orange headers and hope that that makes the application send something harmful back, and the cache will save it and serve it up to other users. But there's a bit of a problem with this approach to cache poisoning, which is that most applications take most of their input from the query string and from the path, and we can't directly edit those with this style of attack. However, this understanding of cache keys is actually a bit simplified. The request line, it is unexploitable because it's in the key, unless someone decides that analytics parameters are hurting performance and they need to rewrite the query string. Or the cache decides it's going to normalize the request line because, normalization is great. Or the cache key components are stored next to each other as unescaped strings. Or there simply is no cache key. Any of these can cause trouble for your application, as we'll see shortly. Because this approach to cache poisoning is built around exploiting specific unique quirks in the target system, the first step to an exploit is to get an understanding of how the target cache works. If you can't do that, you don't stand a chance with any of these techniques. And to gain that understanding, we need the help of a cache oracle. This is just a term I've made up for a page on the site that we're going to ask a series of questions to in order to understand how the cache works. This page needs to be cacheable, and it needs to tell us somehow whether it got a cache hit or a cache miss. This could be headers, or it could just be the speed with which the response comes back. And in theory, those two conditions are sufficient, but it will also make life easier and let us find some more advanced attacks if this cache oracle page also reflects the whole URL and reflects at least one specific parameter. Having chosen this page and got hold of any documentation or source code that you might be able to find, the next step is to ask a series of questions to this oracle to understand what's happening. The thing to focus on is look for transformations that are happening on your request in order to create the key. Things like, is your request being normalized when it's stored in the key? How are the components being stored in the key next to each other? Is there some kind of URL parsing that's happening before the key is generated? And so on. We'll see some example of where these go wrong shortly. Having found hopefully a few quirks in the target's cache, the final step is to find a gadget to chain this with to create a powerful exploit. This could be an existing vulnerability on the target where we can just increase the severity of it by combining it with cache poisoning, or it could be something that's completely harmless by itself. And that's the theory. So now I'm going to show you the kinds of things that you might run into when you apply that methodology to real-life systems, starting out with some really simple scenarios, and then things will get progressively crazier towards the end of the presentation. Here's a nice simple example of how to apply the methodology based on a real target that I found. For our oracle, we're just going to use their homepage because they've got this header that tells us whether we got a cache hit or a cache miss. That makes life easy. And they're also reflecting the host header, which is where we're going to put our payload. What we're going to do is we're going to ask the question, is the port in the host header included in the cache key? So we're going to send a port of 1. We see it get reflected back to us, and then we're going to replay that request byte for byte identical, but without the port specification. And sure enough, as you can see, we have a cache hit. So that tells us the port is not included in the cache key. And in fact, with that one request, we've just taken down the homepage of that website, because now whenever anyone tries to fetch that page, they're going to get a redirect to port 1, and their browser will just time it. Who does this technique work on? Quite a few companies. There's just one thing to mention before you go charging off bounty hunting with this, if that's your kind of thing. Be warned that as a denial of service issue, you may get a mixed reception. Using this sort of finding on different companies that have bounty programs, I've had some of them saying, we do not care that you can take our site down with one request. And I've had other sites pay me 10K for it. So as with any kind of bug bounties, it's a bit of a lucky dip. Now, one of the most common transformations that people do on the cache key is they simply eliminate the entire query string. And you might think that such a major transformation would be really obvious, right? But it's actually incredibly easy to miss, because what it does is it makes dynamic pages look as though they're static. On a normal page, if you change any parameter, you'll have some kind of visible change in the response. But if the page has a cache which excludes the query string from the cache key, you can change any parameters you like. You can even specify a cache buster, and you'll think you're talking to the backend, but actually you'll be talking to the cache, and therefore your parameters will make no difference to the response. In order to find these pages, we need to take extra measures. One thing you can do is try and put cache busters in HTTP headers that are likely to be included in the cache key, and Param Miner will do this by default as of today's update. This approach works really well on some systems. For example, on Cloudflare, by default the origin is in the cache key, and so this will pierce through their cache and tell you whether that page actually is dynamic or not. But it doesn't work on all systems, because some of them basically ignore all the HTTP headers, or all the ones that we can change without just breaking the application anyway. However, there is a kind of a cheat you can do. On Fastly and systems running Varnish and various others, you can use the purge or fastly purge HTTP methods to directly delete entries from the target website's cache with no authentication. This feature is fantastic for launching cache poisoning attacks, but it's also great for simply piercing through the cache to find out what's really going on with the page behind it. If that doesn't work, well, there is an option of last resort. It kind of sucks, but you can take advantage of the fact that a lot of caches do only really lightweight normalization on request paths, whereas servers and frameworks especially tend to do much heavier weight stuff. So that means you can send requests that the cache regard as being different. They generate a different cache key because the path is different. But once the backend server's finished processing them, they end up hitting exactly the same endpoint. I've thought about putting this technique in Param, and by the time you watch this, it may have happened, but it is a bit unreliable, so we'll have to see. What happens when you try this technique out? Well, you're going to find some really obvious vulnerabilities. For example, on this online newspaper, I found reflected XSS on every single page, including the home page. And this is a site that has a bug bounty program. Normally, a vulnerability that obvious wouldn't last 5 minutes, right? But because of the cache, no one had found that vulnerability. They just talked to the cache and probably concluded that this site was static. But there's a second effect, because our payload here isn't part of the cache key. So that means having sent that request myself, shown there, from that point onwards, as long as I time that right so it hits the back end, anyone else who fetches that page is going to get my payload coming back at them. So in effect, with this reflected cross-site scripting, I've gained persistent control over every single page on this website. Now, at this point, some of you are probably thinking, well, that company is just stupid. They're playing with caching, but they've got no idea what they're doing. There's no way that could happen to anyone who knows what they're doing. And to counter that point, I'm going to use the same technique on the main website of a caching vendor called Cloudflare. So here, the gadget that we're using this time looks pretty much harmless, right? All they're doing is they're taking the request and query string that we give them, and they're putting a slash on the end of the path, and just like the previous target, they've excluded the whole query string from the cache key. What we're going to do is we're going to take advantage of that extra / that they're sticking on. So we're going to send a request that uses a really long query string to mean that the resulting request line is the maximum length that their server will allow. And then they're going to give me a redirect that takes that maximum length and puts one extra character in it. So then, having done that, if I time that right, then from that point onwards, if anyone else is browsing Cloudflare's site and they press that login link, they're going to get this cached redirect that includes my really long query string. And when they follow that redirect, they're going to get blocked by the server because their request is too long. So with one request, we've persistently taken down Cloudflare's login page. It's worth mentioning that you couldn't send that last request by itself directly as a cache poisoning attack because Cloudflare would refuse to cache it because of the HTTP error status code. It's the layer of indirection that the redirect adds that makes this issue exploitable. So I reported this to Cloudflare, and they could have obviously patched it on their site really easily, but they acknowledged that this was probably going to affect most of their customers as well. And so they deployed a kind of more general mitigation. They said, in the cache, if the query string is unkeyed and the query string in the responses location header matches the query string in the request, just refuse to cache that response. The concept behind this is completely sound, but I was able to bypass it by encoding a single character in the request because the server would decode it and therefore it wouldn't match. And Cloudflare has now fixed this, but obviously if you have any other transformations happening in between the query string of the request and the location header, you'll once again be able to bypass this mitigation and take down a whole bunch of pages. So far, we've seen how simple transformations can have quite major unexpected effects. But on some sites, you'll find even the transformations themselves get quite messy because they've decided to exclude specific parameters from the cache key. I've seen this happen with UTM content quite a few times because it's an analytics parameter. It changes a lot and it's not really relevant to the backend. So for performance reasons, they just exclude it from the key. And obviously, this makes full URL reflection-based vulnerabilities really easy to exploit. But what happens if they've got this behavior and you find a vulnerability in how the parameter term is handled? Can you combine that with this cache poisoning issue to escalate the severity? Well, in theory, you can't, because the term parameter is meant to be included in the key. But actually, it depends on the implementation. This is where cache parameter cloaking comes in. Some people are going to implement these things by Googling them, landing on Stack Overflow, and then implementing a regex. That's how I would implement it, at least. And if someone's using a regex like this, well, this one's meant to eliminate any parameters called underscore from the cache key. Given that behavior, how can we place a payload in the parameter queue? Well, just like so. So here, the interesting thing is that they've eliminated this parameter from the key, but they've substituted it with a question mark. So although we can append arbitrary things to arbitrary values, arbitrary parameters on the site, we can only successfully poison parameters used by the site that already have a question mark in them. These kinds of complications can arise fairly often with this type of issue, and they generally just make life more interesting. Here, I've hit a fairly humble target, right? It's just a Stack Overflow post, but this also works on some more serious companies. Remember how we got Akamai to show us a few cache keys, and some of them had this Akamai transform parameter, and some of them didn't. That means maybe they're excluding this from the key. And if we send a request with that parameter, we'll see it doesn't appear in the true cache key. And if we change the value of that parameter, then we'll get a cache hit, which confirms it is genuinely not in the key. And the cool thing here is that their parsing of the URL is not quite optimal. So as well as being able to add this value to the query string, we can also append arbitrary payloads to arbitrary parameters of our choice using this technique here. So here, what the backend sees is one parameter called X containing our payload, but Akamai will eliminate the question mark and everything after it from the cache key. This would be extremely serious if it wasn't for one small catch, which is that there's actually an invisible bit not mentioned in any of the cache keys that says, did this request contain the parameter Akamai transform? What that means is that you can only use this technique to exploit sites that are already using the Akamai transform functionality. You can't hit arbitrary Akamai targets with this. On a different target, something was weird and I couldn't find an oracle that was any good, so I looked at the code in order to figure out how to exploit it. And we could see they were splitting the query string on semicolons as well as ampersands. So that meant that in principle, I could use a payload like this to smuggle a malicious bit of code into the callback parameter that would be excluded from the cache. And I thought, great, I'm going to set up my demo using this because the vulnerable cache here is rack cache, which is something I can easily set up myself. I set it up, I tried it, and it didn't work. And it didn't work because Ruby on Rails itself also splits parameters on semicolons as well as ampersands. And that is good news for rack cache, although we're going to hack it in a different way shortly later. But it's bad news for Ruby on Rails, because it means if you use an application built on Rails behind any normal cache, like Varnish or Akamai or whatever, and you eliminate any parameter from the cache key, then an attacker can exploit that to make arbitrary, unkeyed changes to arbitrary parameters on cacheable pages on your site. For example, in this request here, from Akamai's point of view, from the cache key's point of view, there's one parameter called callback, and the value is legit, or whatever value the application happens to be using. But when Rails parses this, it sees three parameters: the callback, UTM content, and a second callback parameter. And it prioritizes the last parameter, which is something as an attacker we have full control over. So we can just change that to whatever harmful code we like, and then any page on that website that uses that JSON-P will end up being exploited. So say you found parameter cloaking using any of those techniques. The next step is to combine that with a gadget, right? And as we've seen, traditional XSS works great, but if it's a hardened target, then you might not have that. But the good news is there's a whole bunch of other things that are harmless by themselves and therefore less likely to be patched, that still become harmful in the presence of cache poisoning. And JSON-P, as we've seen, is one of them. But also any kind of dynamic content in JavaScript files or CSS files. Typically, this stuff is harmless. But with cache poisoning, we can poison these resource files so that any pages that reference that resource file end up being exploited. For example, I found a CSS file on one target they reflected the query string in an import statement in that CSS file. And by changing the query string, you could break out of the import statement and import an arbitrary malicious CSS file from your own site in order to steal sensitive information from any pages that referenced that CSS file. In fact, if the page that uses loads a CSS document doesn't have a doc type, then you can even persuade the browser to load HTML responses as CSS, which can enable exploitation of normally static CSS files. And there's also major implications of this issue that make relative path overwrite issues substantially easier to exploit. However, unfortunately, it takes about 20 minutes to explain, so I'm just going to leave that one for the white paper. Now, another way of hiding parameters from the cache is simply to send a post request. This is unbelievably simple. I was quite surprised to find this worked, but on this Chinese mapping site, I found reflected XSS on every page if you use post. You had to tweak the payload slightly to bypass their WAF. That's why that looks weird. And the cool thing was they weren't including the request method in the cache key. So having sent that payload, if someone sent a GET to that site, just browsing the site as they normally would be, then they ended up being exploited by the poison cache. And just like the earlier XSS issues we saw, this one was present on every page of the site, so I could take persistent control over the entire website. I actually had a research collision with someone else with that. They were using the same technique around the same time. So they've just published a blog post coming out today, hopefully. And if you check that out, you'll find some more examples of this technique. Now, there was a collision there, right? But with a small tweak, we can make that approach work on a lot more systems. For inspiration, let's look at the Varnish documentation. They say, if a request has a body, this will be sent to the backend. The default Varnish config removes the body for GET requests because it is questionable if these requests are valid, but some applications use them. So what happens if you're using a Varnish config file that doesn't have this snippet? Well, unfortunately, GitHub didn't have this snippet, and they were using Ruby on Rails, which does accept parameters in the body of GET requests. That meant that on cacheable pages, I could make arbitrary changes to arbitrary parameters. For example, with this request here, I've poisoned their report abuse page. So if you try and report abuse on my profile, it ends up reporting somebody else. You could also apply arbitrary filters to hide issues in people's projects and such like, and also just block access to the majority of project content using this technique. So I reported this to GitHub and got a 7.5K bounty for that, which was pretty cool. In addition to working on some varnish systems, this technique also works in exactly the same way on quite a few people using Cloudflare. And on one of those, I had a really hard time finding a gadget to combine this behavior with. In the end, I used a local redirect on their login page, so that if you went to their login page, entered your creds and logged in, then you would get redirected to the logout page, which would then redirect you to the login bouncer and log you back into my account using my authentication token, and then eventually put you on a page of my choice. So from your point of view, you enter your creds, you press login, and you end up logged in, but you're actually in my account. And unfortunately, I can't describe the nature of the site, but if you were to then proceed to do something on the site, I would have full knowledge of what you've done there, which could be quite interesting. I reported this. Sorry, that makes it sound like it's a certain kind of site. It's not that kind of site, you know what I mean. I reported this to Cloudflare, and they said that they're not going to change this behavior. But I've completely lost my thread now. But they did update their documentation to say don't trust GET request bodies, which basically means don't use Rails. There's an interesting kind of side point here, which is that this gadget that we've seen, that we've used on this site and on GitHub, is an incredibly powerful gadget. It can make arbitrary changes to arbitrary parameters, but neither of the exploits were that harmful. And that's because neither of those sites had the right kind of gadget that you could use to make a high impact exploit. So how hard these cache poisoning issues hit you is massively dependent on whether you've got these kind of almost exploitable vulnerabilities present on your site. So I use Firefox for most of my testing, and every year I'm doing my research and I accidentally find a vulnerability in Firefox's update infrastructure. And this year is no different. This one is going to show us how something even as simple and common as normalization can be really quite harmful. If you look at the Nginx config on download.mozilla.org, it looks fine. If you look at the proxy cache key documentation, you'll see their key is very similar to the default Nginx one. But if you look at the proxy pass documentation, there's a kind of a clue that something might be wrong here. It says if you use proxy pass without a URI, like Mozilla have done, then the request URI is passed to the server in the same form as sent by a client when the original request is processed. What that's hinting at is the fact that this proxy cache key value is being normalized, but the value that gets passed to the upstream system is not being normalized. What does that mean? Well, whenever you open a Firefox and periodically thereafter, it checks for important security updates that need to be installed to keep you safe. And it does that with a URL like this. And if there's a security update present, it'll give you a redirect to the installer. But what happens if I send a request that looks like this? It's byte for byte the same, but I've URL encoded the question mark. Well, Nginx is going to URL decode that question mark when it saves its cache key. So from Nginx's point of view, this is a completely valid check for updates. But when the backend server sees the unnormalized version of this request, they interpret the whole thing as being the path, so there's no parameters, and it breaks the redirect, and in practice, the update fails. So if I send that request and time it right, then whenever anyone else checks for updates for Firefox, they get this broken redirect, and I've just disabled Firefox security updates globally. I think this is my favorite denial of service issue that I've ever found. What else can you do with normalization? Well, there's a classic issue that I'm sure many of you have run into, where you find some XSS, maybe it's in the path, or more recently, maybe even in the query string, And it looks great in Burp, but when you try and exploit a browser with it, it doesn't work because the browser is encoding your payload and the server is not decoding it. But with normalization, this issue once again becomes exploitable because you can send your request shortly before the victim loads the URL you give them, and they'll just get a cache hit from your request. They'll get your poisoned response and they'll get exploited. On the topic of issues that are normally unexploitable, what do you do if you get cross-site scripting in a HTTP header that's in the cache key? Normally, that's useless. But on Akamai, they stick both query parameters and headers into the same chunk of the cache key. They separate them using underscores, and underscores aren't escaped. So that means these two requests have exactly the same cache key. So as an attacker, I can send the first one with the poisoned origin, which is something no browser would ever agree to send. And then I can hand the URL of the second request to my victim. They'll hit that, they'll get my poisoned response and get exploited. After seeing how easy that was in Akamai, I thought I'd try it on Cloudflare. According to their documentation, the cache key looks like this. So these two requests should have the same key. However, in practice, it doesn't work. And I tried a few things, ran low on options, and eventually sent an email to Cloudflare to complain that their documentation is incorrect and say, could they fix it, please? Unfortunately, one thing led to another, and I had to explain the attack. And then I got a response from their security team saying, well, the documentation is wrong. The attack you're describing is possible, but you're doing it wrong, and we're not going to tell you how. And then they have now patched it. But they did send me a t-shirt. So it was possible to use some variation of this on Cloudflare, but unfortunately I can't tell you how to do it. On the opposite end of the spectrum, some attacks are so practical that it's not possible to do them safely. On Adobe, I was testing for a classic cache poisoning issue on a particular blog page on their blog, and I suddenly got a flood of loads and loads and loads of traffic to my server. And it turns out, unfortunately for, well, me and Adobe, they were using an internal and application-based cache that was integrated into their application and had no concept of a cache key. So I poisoned the header of my page, and that header was then being used on every page on the entire website, including their homepage. All the resource loads went to my site, and all the links on their homepage also sent people to my website. This was not a great experience for either of us. I reported it very quickly. They fixed it very quickly. Luckily, they were quite understanding. But you can see this kind of issue makes the distinction between a legitimate-ish researcher and an attacker really quite blurry. And not only is internal cache poisoning uncontrollable, it can also be invisible. On a different time, I had an idea for a denial of service detection technique, sent it to a bunch of sites, and got loads of traffic from the Department of Defense intranet. Eventually, I think I figured out what happened, which is there's this site, it's meant to be internal to the DoD. Any attempt to access it from external redirects to their intranet, which I can't access. The denial of service technique breaks the redirect. It only lets you access the error page though, but hitting the error page with a certain payload poisons their internal cache and thereby poisons all the resource loads in their intranet administration interface. So I can't tell you how to find internal cache poisoning issues safely, but I can tell you how to recognize it to avoid wasting your time. If you see both old and new values coming back in that one response, that's a good clue. Or reflection of your input on different pages, or things just don't make sense. And I haven't yet figured out how to do it completely safely, but if you're doing any technique of any type, then this might happen by accident. And what that means is whenever you use a domain, whenever you give a domain to the target that's not the real target domain, please use a domain you control. You do not want to be sending all of your target website's traffic to evil.com unless you are the lucky owner of evil.com. So I was going to release a standalone tool for this research, but instead I've done an update to Param Miner, which is the open source Burp Suite extension that I originally wrote for my prior cache poisoning research, it can find almost all the techniques mentioned in this presentation, and there's a demo of me using it to exploit a fat get vulnerability in rack cache on the GitHub page. Please check it out. As far as defense goes, the key thing is, if you want to make these optimizations, just rewrite the request, not the cache key. This is vastly safer. Also, don't accept fat get requests, don't use Rails, I guess, or see if you can patch it. And if you're using caching, it's really important to patch unexploitable vulnerabilities. Now, there's a whole bunch of more information on this. Check out the white paper which I've just published, which has a couple of extra techniques. Also, the prior research is well worth reading if you haven't already seen it. And if you're watching this at Black Hat, check out Amit Klein's presentation on HTTP request smuggling, because he invented it back in the day, so I'm sure that's a good talk. This is not the end of novel cache poisoning issues coming out. I've got loads of leads, and I'm sure other people do too. So please don't think this is a comprehensive presentation. And that basically means the most important thing to take away is that caching introduces unique hazards, and these may be well hidden and not documented by anyone anywhere ever. And as such, if you're using caching, unexploitable vulnerabilities are really worth patching. I'm going to take 5 minutes of questions now. If you have any more after that, feel free to chat me an email. Don't forget to follow me on Twitter, and thank you for listening. Cool. Thank you for listening. I hope you enjoyed that. Does anyone have any questions? If you do, if you post them in the chat box, then I'll be able to see and answer them. The one thing that I need to add is that Akamai would like me to tell you that they're working on a fix for the Akamai issues mentioned in this presentation. Cool. Doesn't look like you've got any questions. Great, thank you for listening. Don't forget to check out the Academy Labs and the white paper, which has some extra techniques stuck in there. We've got one question. When I'm testing, cool. So the question is, when I'm testing on live sites and I accidentally get persistent XSS, how much do I disrupt the business? Well, when you're testing for most of these issues, you can just use a cache buster, and what that means is that you'll cause no disruption for anyone, because you're only poisoning a specific URL that other people aren't visiting. The only exception to that is the internal cache poisoning. Internal cache poisoning, as I mentioned, is really dangerous, and you can't do much about it really. So it's only happened to me twice, and the site was basically defaced until their team manually fixed it, I think, which is one of the reasons that I didn't talk very much about internal cache poisoning, because I can't properly research it until I figured out how to do it without causing business disruption. But most of the techniques in this presentation are completely safe as long as you use a cache buster. The other question is, do I have LinkedIn? No, I don't have LinkedIn, but I am on Twitter. That's my version of LinkedIn. And I think that's everything. Cool, great. Thanks for listening.